Hey y'all, Hobby here. I am the team captain of the 2020 Pumpkin Reapers team at KSU's annual Pumpkin Lunch. We built a Trebuchet this year that took 3rd place and shot an 8-pound pumpkin 191 foot. I'm making this video because I felt really blind going into this project. There weren't a whole bunch of resources available. And I'm incredibly proud of the work we've done so far, so I just wanted to share it and maybe provide a resource for some students going forward. So this will be a complete reflection and analysis of, how we built our machine and what we could have done better, as well as what I saw there. So get started. We were the Pumpkin Reapers. Our need was to establish that Halloween was the best holiday of them all. We set up an initial working criteria. We wanted to spend around $500 and we wanted to shoot at least 100 meters. So now we kind of have like our specifications, and now we came up with solutions. How can we achieve that goal? So the first thing we came up with was a pressure cannon, big old air tank, uses pressurized air to shoot a pumpkin. These have incredible range potential. It's relatively simple, being that it doesn't have many moving parts. We didn't deem it very safe though. Anything pressurized is going to be volatile and unpredictable. So wasn't safe, predictably inaccurate, and steel is very expensive, especially pressure rated steel tanks. Just completely made this non-viable. The next thing we considered was a ballista. Predictably, you can crank this down to a specific point each time, so it's predictably consistent. Like, you'd think it would have been accurate, but we strayed away from it because it was incredibly complicated. Even I saw there was a team this year that used leaf springs to do this, and it was incredibly difficult, complex to build. It did not shoot very far, and the springs and cables under tension definitely detracted from the safety. Slingshot. So Slingshot, we considered it. It's incredibly cheap, incredibly simple, relatively safe, but it's inaccurate and it has no range. So then continuing to go up, we considered the Whipper Trebuchet. It has good range, it's efficient, relatively safe, okay cost, definitely starting to get up there. So the cons to this is that there's more moving parts. You can see they've got the pumpkin up here. They've got their counterweight over the top, so they'd have to pull this down, and it would hinge over the arm, and this would fall. And it's a pretty complicated machine. I don't have a picture of it here. I'm gonna throw one up on the screen. But another version of this would be the floating arm trebuchet. It is incredibly efficient, and it's very complicated. It's got a lot of moving parts. I didn't totally research it or understand it myself, so I didn't consider it. It was just too complex for my team. But it is definitely, if you have a very involved team, that would be a good thing to look at. So then our last thing that we looked at, this is actually my machine here, was the traditional fixed trebuchet. It has good range potential, all things considered. It's relatively safe. There's nothing under tension. The only thing you have to worry about is kinetic energy from this arm coming down. Okay in cost relative to other things. Few moving parts, very simple. And then the cons is it's predictably inaccurate. We're basically just chunking it in a direction. So here was our decision table. We valued safety, simplicity, range, accuracy, cost, and total. One thing I really want to drill into, if you're another KSU student going into this project, you have to consider manufacturing and cost constraints. Manufacturing constraints are going to be your teammates. It's difficult. I mean, to put it simply, is you have to understand that this is a freshman class at a university with very little gatekeeping. Anybody can take this class, and anybody can decide that it's not quite for them halfway through the semester. So you really have to evaluate your teammates and decide, how involved are these guys going to be? Do they have any construction, any fabrication experience? Are they passionate about this? Or are these guys, here to like really work on this with you, or are they just there to show up? And that'll kind of dictate how much you can do with simplicity. At the actual pumpkin launch, I saw a lot of machines that were overthought and under-engineered. Basically, I really want to drill on a simplicity. I probably should have ranked this higher in reflection. You want to build within your constraints. If you have, only one or two guys actively participating on your team, you want to go for a simple machine that you can build and design well, instead of going for like a floating arm or a whipper trebuchet that you kind of fail on. There was a lot of whipper trebuchets at the pumpkin launch this year, and I saw several of them collapse. They were not well built. So please rank complexity or simplicity, building constraints high. That's a very big factor. Range and accuracy. So there's two win conditions for the pumpkin launch. You can either most consistently to hit 30 meters, or who can throw the farthest. We considered either or win conditions, so we ranked them 15% together. And then of course cost. Who's on your team can you as college students afford to build this? I'll touch more on that later. So this is, we started at the bottom with the pressure cannon. We deemed it was relatively unsafe and incredibly expensive. The Ballista was kind of a, it had potential for accuracy, but it wasn't that safe, and it was kind of expensive. Next up, we had Slingshot. It was incredibly simple, very cheap. We ranked its accuracy kind of high, but in retrospect, it's not. Range, very low. It's just basically human powered, maybe some ropes or some springs, but it was, I wouldn't advise it. Whipper trebuchets, like I said, if you have a very involved team, it has incredible efficiency. It can throw very far. It's not very accurate, and the traditional and the whipper, all things considered, probably have about the same cost. For me to have built my trebuchet as a whipper, or I'm not sure about a floating arm, but as a whipper, it wouldn't have been much more. It would have been marginal. It's just the complexity between the two. So if you have a more involved team, go for the whipper. If not, try to build simple. Okay, so going on to the design of our machine, there is a research report by David B. Ciano. I'll have it linked in the description, or my work cited at the end. But he's basically this physicist that developed a lot of the mechanics and really evaluated trebuchets. So he came up with a few optimization, like general rules. Your payload arm should be 3.75 times longer than your counterweight arm. So this arm right here, the longer one, you want that to be 3.75 times longer than your counterweight arm, which is what's going to be on this side of the fulcrum. So obviously with the trebuchet, your arm is going to rotate around this metal bar right here called the fulcrum. So then the next thing is that the sling length should be about equal to the payload arm length. So you've got your payload arm, which is the side that's going to throw the payload. So from the fulcrum to the tip, you'll measure that out, or however long you designed it for, and you want that to be about how long your sling is. Another optimization he had said about trebuchets is that the initial counterweight should be about 45 degrees above your fulcrum. So our actual design did vary. I'll show you some more pictures in just a second. The way we originally built this was we had a 2x8 frame, and then everything would kind of bolt to the frame. So if you could square this frame up, then you could run a bolt through the side of the frame, and that would bolt up. And then it's a little bit more complicated up here. You would kind of have to get a bolt to sit flush against this, you would have to drill down at an angle. You can't drill straight through these supports and the main post without countersinking something, because it's at an angle. It's not going to be flush on one side. So so we had our main post here. We had a frame. We had everything bolt to the frame, and then it would kind of screw or bolt into this. Notice I'm saying bolt and not screw. I don't think that any kind of wood, like regular screws, I mean, it's all relative to your, the size of your machine. If you're building a big machine like we did, wood screws are not going to cut it, nails are not going to cut it. You want to use lag bolts or a threaded rod, which I'll talk about in a second. So this is kind of the general layout of our machine. One thing we did that other teams didn't do is a lot. You see the stereotypical A-frame machines. We strayed away from that because when you fire this machine, if you really think about it, all this weight is coming down around here and it's getting dropped. And what happens is this end of the machine comes up. So A-frame machines, yes, you could build this side out longer, but the way we kind of approach this is that we wanted to build it longer this way, and we could add weight here. Because when you drop this weight over here, this side's going to come up. And I saw it happen with some other machines at the pumpkin launch. They dropped their fired their machine. This lifted up, and then their arm actually hit, or their sling actually wrapped itself around this piece on their machine because it lifted up, and it was a mess. But so that's how we designed that. Our arm, we designed a pretty heavy-duty arm. We designed it using 4 pieces. So what we did is we took 2x12s and we sandwiched them together. So you got 3 in the middle for strength. And I'll show you some more pictures in a second of the actual version. But for strength, we pretty much sandwiched these together. And then we had our arm, the little 2x4 here, be our final payload. The reason you want to do it this way is because anything on this side of the fulcrum is counterproductive. This side is where all of your energy comes from, so this side is coming down, and then this side is going up. So you want to have as less weight as possible on this side. So materials. So cost of the machine. So this is a picture of our shopping cart here. So we had 6x6 main posts. We used some 4x4 supports. We actually ended up building the frame at a 2x12s instead, make it a little bit stronger. Fulcrum and payload holder. So if you're building a trebuchet, you're gonna need a fulcrum, right? Like you need something for your arm to rotate around, which is this metal bar right here. I can't stress this enough. Make sure your arm is strong enough, or your fulcrum is strong enough relative to what you're building. A lot of the machines at the day of the pumpkin launch bent or broke their fulcrums. Do not use, if you're building a big machine, do not use, pipe, like black plumbing pipe. Don't use that. Definitely don't use conduit. And don't use rebar or threaded rod. I'll tell you where to get it in a second, but you can get 2-inch cold rolled steel round bar. I think we got 7 foot of, I'm talking like solid, like 2-inch diameter steel for $80. So that served as our fulcrum, and it's what our weight rested on. So about 7 foot of that was only about $80. So take that into consideration. That is definitely a weak point for a lot of people. So get some real steel for that. Fasteners. So like I said, we did not use screws. We used bolts. And bolts are expensive too. So we actually bought threaded rod. They sell it like 5 or 6 foot at a time at Home Depot, 1/2 inch, and we just bought washers, fender washers, and nuts. So it'll go on kind of like this. Your fender washer will go on first. That gives it a big surface area. This lock washer, it's got a little split in it, so when you compress that, it kind of acts like a spring, and it stops your nut from backing off. So it's a 3-piece system. Definitely something to consider. Cabling. So we abandoned these supports in favor of cable. Let's see. So here's some more pictures of my machine. We used cabling instead of those 4x4 supports. So 1/4 inch steel cable, 100 foot, about $40. They come with these little clamps, and then you'll need eye bolts to wrap it around. Those are about $3 a piece. So this is about price per item. Slings. So we made a little tarp. I'll have pictures of that in a minute. But basically, our sling was made out of tarp. We got some grommets from Harbor Freight, some paracord, and if your grommet kit isn't that great, ours actually ripped out. I just went to Home Depot and bought some Gorilla Tape, and then I poked a hole through it with a screwdriver, and this stuff is incredibly strong. You could definitely fabricate some kind of sling out of tarp and grommets, and then just duct tape or Gorilla Tape. Gorilla Tape's stronger than duct tape, so Gorilla Tape over your grommets or wherever you're going to be pulling from, and that might work out. Some consumables we had. Oh, here's the steel bar I was talking about. So we use paddle bits. You'll use that to drill rougher holes in wood. Drill bits you'll use to kind of clean out the holes. These are, if you have a lot of drilling to do, these are much more efficient than these. These take time and wear down sooner. These are pretty great if you have a lot of holes to drill. Sawzall blades, so you can use a sawzall or a grinder to cut your threaded rod. We used sawzall, found it, you could do either or, they both work. And then we used a giant hole saw to drill the holes in our main supports for our fulcrum. So here's some pictures of our actual machine. I'm just going to kind of walk you how we designed it. So these are two overview pictures of our machine. We've got our two 6x6 posts with our metal fulcrum right here, our weight holder, our arm. So you have to have some kind of safety strap for your device. So we put two eye bolts on either side and some eye bolts on the arm and ran a strap over. You can see we ran our steel cables instead of front and rear wooden supports. We found these to be easier. So here's a close-up of the arm. You can see we just sandwiched them all in with a bunch of bolts. There's another close-up of our safety strap. So here's what we did in the corners. You can tell we just cut some 4x4s into the corners, and we that's basically how we join the pieces of wood so it would be strong. You could try to run some screws from here to here, but what you might run into that is then your machine might rack because you only have two screws in it, so then they could bend or pull out, or we just found it would be better to put a piece in the corner, and then you can drill into it or screw into it from either side, and it's much more stronger. And then the other thing we did with the steel cables is they did loosen over time, but when we first started, we started with this eye bolt all the way loose on both sides. So then we, hand tightened the cable, and then we ran this up with an impact, and basically we used these eye bolts to tension the cable. Here's some more pictures of our machine. You can see 2x12, 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 and then right here, these 2x12s keep going, but that's where it splits into our 2x4. And then here's another picture of our machine in the driveway. So our sling and firing pin. So looking at the arm and its down position right here, you have to have some way to release this. So what we did is we'd load our weights, we'd unstrap it, and then we'd have a screwdriver or something you can pull out in here. And basically all we did is we took a screwdriver that lined up through these three holes, and we put a strap around it, so when we had to, we could take the safety strap off the arm and then yank this out, and then the machine would fire. This right here was our sling. We just used some Harbor Freight tarp, paracord, and grommets. You can see I duct taped all of our holes. So we just kind of laid it out flat, and then we did a grommet in each corner, and then we pulled the middle up, and we went through the middle. So that way it kind of sandwiched it. It's hard to explain, but if I took my piece of paper right here, it would be like we creased this middle piece. Let's see if I can do this. Oh, maybe I can. So it's like we crease this middle piece, and then we take the corners and we run it like that. And now you kind of have like a little cradle. You do that to both sides. Our medicine ball that we were practicing with and our pumpkin fit beautifully. Okay, so I was watching this back and I realized there was a few things I forgot to mention at this part. So side supports. So you can see right here we've got a 4x4 on the bottom with a 4x4 running up. You don't see it in these pictures because we had to partly disassemble it to transport it. But make sure your machine has side supports. These machines are not 100% efficient. This will not always go straight up and down. Sometimes it'll go side to side depending on how you build it. So make sure you have side supports to support you on that lateral force. Your track, make sure you have some kind of track for your pumpkin and your tarp to slide over. We use PVC, and the friction between the PVC and the tarp, it worked out great. There was no friction. But make sure you have something. Even if you don't use PVC, make sure you have some kind of plywood or some kind of track, because like I said earlier, some people didn't have one and it got caught in like the support to their machine or whatever. So just make sure you have something that's going to give you, a path. Another thing I wanted to talk about is the angle of your firing pin. You can't tell in this picture, but the reason this is offset some is these are actually staggered. So this is low, this is in the middle, and then this one's actually set up high. So when we had our firing pin in there, is actually in there at like an angle. So when I yanked on it, it came straight out. A lot of people had problems with their firing pin binding. They would take their safety strap up, safety strap off. They would be all ready to fire, and then they would go to pull on their firing pin, and it would be wedged in there. You've got to remember, this pin is holding about 500-600 pounds of force. So if you have your angle bad, or you don't design the firing pin right, it's going to get bound up in there, and it's going to get stuck, and you're going to yank on it, and that's just something to look out for. It's something I did see a few times. A lot of teams had problems with that. So make sure you don't do something straight up and down and expect it to pivot or any mess like that. Try to keep your firing pin simple. So another thing I wanted to talk about, if you're building a trebuchet, so everyone's familiar with Pythagorean theorem. That applies here. A common construction or carpenter trick is the 3-4-5 rule. So you can measure 3 foot down the side of this frame and 4 foot up the arm, or vice versa, and the hypotenuse should be 5 foot. So to make sure that you're building this square, you should measure out on this and then measure up on that, and then you'll see your hypotenuse should be 5 foot if you measure it, and that's how you know if you're staying vertical. The same rule applies to making sure your whole machine is square. So if you measure corner to corner and then corner to corner, if it's a square, your two hypotenuses should be equal to each other. So if you want to make sure that your frame is square, measure corner to corner and corner to corner, and they should be the same. So cost analysis. Here's a fun one. So we spent about $1,100 on this project, but there were some discrepancies. We had a lot of wasted material. Depending on how you cut your wood and how efficiently you measured everything out, you can have stuff left on the side. Trial by design. We had a lot of as-builts. You know, we're halfway through building it, we had all this wood, and then we're like, well, what if we use steel cable instead? You know, it'd make it easier, stronger, whatever. So excessive material, we overbought material in case something broke. The instructions the professor gave us were pretty clear that we should bring extra components. If you're building a smaller machine or under-designed machine, that may be true, but there's nothing breaking about our machine. So we had a lot of stuff to return. Small items, consumables, we did not, we just bought those in bulk. We didn't really track those all that well, we just bought them. I basically got these total costs just from adding up all of our receipts. Personal items, we might have picked up some tools, some consumables that would, you know, stay at the house afterwards. Pretty negligible though. So our source of income, KSU gave us $125 this year to do this project. Everyone in the team pitched in $50. There was 6 other teammates, and then my father's business, Gotcha Security, was able to sponsor us. So that's where our income came from. Assuming minimal waste, theoretical reproduction cost is around $600 to $650. If you multiply, I put all the prices up here. If you take all these prices and then multiply exactly what it would take us to rebuild this thing again, it actually does come out to be about $600 to $650. You also have to remember that we're in the middle of a pandemic right now. Wood prices are incredibly expensive. They're very inflated. So given any other time and a little bit more efficiency, I think we could have hit our budget constraint of $500. But that just kind of gives you an idea of about, you know, what you're looking at. Okay, so here's one thing I want to talk about, because a lot of people coming into a freshman year at a university like this, they don't have a lot of experience with suppliers, you know, where to get equipment, where to get tools. So everybody knows Home Depot, you know, really big box chain store. They're great for building materials. You know, you're going to find all your lumber, your threaded rod, etc. there, all your hardware. But if you need to purchase any cheap, you know, one-off tools that you're just using for this project, I would not suggest buying them from Home Depot. They have very good tools. You know, the Husky, Ryobi, Milwaukee, they're all very reliable and great tools, but there's cheaper stuff out there. So Harbor Freight, anything cheap, consumable, you know, saws, whatever, I would suggest getting that from there. If you want to buy some power tools, if you don't have any access to power tools and you want to buy some for this project, maybe you'll keep them down the road. Try out some pawn shops. Lots of pawn shops have older, you know, corded tools. You know, they might be 5 or 10 years old, but, you know, they're still going to be Milwaukee, Rigid, DeWalt, you know. They're going to have good tools at a very discounted rate. So if you need any power tools, check out some pawn shops. If you need any hand tools, check out Harbor Freight. So everyone's heard of Home Depot. Ace Hardware and Tractor Supply. You know, they're going to have some miscellaneous stuff in a pinch, like, you know, some chains, straps. You know, they might have some hardware. You can check them out. Metal Supermarkets. This is not a well-known place. And they have 3 or 4 locations around Atlanta, and they sell metal to... They sell scrap metal. They're a big metal supplier, but they sell to the public. So I walked in there and I bought 7 foot of steel bar, you know, for $80, and they cut it for me. This is, if you need any metal, check their website out. They have pretty much everything you need. 2 other things not a lot of people know about going into this is McMaster Carr and Granger. These guys sell manufactured components such as like shafts, roller bearings, anything like you need like to be precise and manufactured. Go to McMaster Carr or Granger. So here at Projectile Motion, you'll see from David Biciano's and the other report I linked in our description, trebuchets have a lot of different, have multi-dimensional forces and different rates of change. So they're typically recognized or calculated using Lagrangian mechanics and second-order differential equations. That's pretty out of scope for this Intro to ME class, so we pretty much just did our best. So someone was able to come up with 43 meters per second as our initial velocity, and we plugged those into some basic physics equations, and then threw it into MATLAB to produce some graphs. That's our calculations. Some what-if analysis is all safety, don't get hurt, what to do if you do get hurt. So reflecting back on our design, we had a very stout machine. You'll see we built it very strong, nothing broke. We had over 20 launches on it. A lot of people there only fired their machine a handful of times until it broke, so I was really proud of that. There's definitely more in the tank. I'll show you some videos of it firing. We had 675 pounds on there, and this thing just took it like a champ. So to get more out of the tank, we would have to increase weight capacity somehow, either by adding more weight. So to add more weight, we'd have to go wider, or we'd have to make some kind of hinged counterweight system. Because the way we built this machine is that we only built it, so this is a great representation right here. We only built this machine 3 foot wide in the middle. So we had enough room for about 6 or 7 plates on the inside on each side, in addition to our arm. So this was definitely a handicap for us. The reason we built it so narrow is the wider you go, the more stress is going to be on your fulcrum. So we wanted to make sure we kept it narrow so we didn't have a lot of strain on the fulcrum, like a lot of bending motion. But what we ended up doing is we ended up handicapping ourselves, because then we maxed out the weight. Like, we physically could not add any more weight to this arm the way we designed it, which was unfortunate. So going forward, I would have built it a little bit wider. What we also could have done is we also could have turned this into some kind of whipper-style trebuchet and actually made the weight hinged and rotated it up. So instead of making the machine wider, we could just make it more efficient with the use of our weight. Height versus distance, you'll see in the videos, our release angle wasn't quite dialed in. Our machine was still launching it very high. We got some decent distance out of it, but we had a lot of wasted energy going up instead of out. Loading efficiency, so if So the way we built it is we had to actually get on ladders. So we put the arm down, we put our safety strap on it, put the firing pin in, and then we get two 8-foot ladders, and we'd have to have 3 people on each side load weights up onto the arm. And it's very inefficient, because then once we fired and the arm was back in the up position, then we'd have to get under it and unload all the weights, crank the arm back down, and then reload it from a ladder. So next time I would include some kind of winch or like an eye bolt on it, so we could just put a ladder, hook a bolt, hook the cable to it, and then winch it back down. Throw our safety strap over, and make a much quicker and more efficient reload. To comply with rules, our sling was permanently fixed to the arm on one side. We basically, so your sling had 2 strings coming off of it. One was screwed into the arm, and then the other one slips off for your releasing. Well, we had one permanently fixed. And being that it was permanently fixed, if the arm is up, you can't reset the pumpkin because your sling is just hanging. So as it comes down, then you can reset it. But as it comes down, your weight's going up, and you're not allowed to get under the weight. So, yeah, so we would have had to come up with like a detachable sling that we could reset the arm and then just hook the sling back on with. So this was my team right here. We had Dylan, we had Gunnar, we had me, we had Yua, Gregory, Sean, and Trell. These were some of our roles. I was the captain, Sean was our safety officer, Yua was our communications specialist, Gunnar was our systems engineer. I'm incredibly thankful for my teammates. They really helped me out a lot. I've got Dylan, who's our logistics manager, Gregory, and Trell. So here's some of the work cited. So scholarly report. So this guy wrote this report as his honors, as his thesis, physics major. That's worth giving a read. He talks a lot about the different mechanics of the trebuchet, and that's where we got some of our calculations and formulas from. David Donald Biciano. Definitely check this out. You can find it on Google Scholar. He wrote like a 50-page report on the trebuchet mechanics. YouTube, so Tom Stanton, check his stuff out. He built a whipper trebuchet, really optimized it. Concerning Reality and Rabbit on the Moon, they both built like trebuchet physics tutorials. The Hurl.wikidot and Pumpkin Chunkin, those are great places. They're basically professional pumpkin chunking competitions. They have like different resources for different types of trebuchets, and or different types of launchers. So you can check those out and get some inspiration and some ideas. Okay, so this video was quite a bit longer than I had meant for it to be, but I'm okay with that. I think I went over a lot. I'm hoping this helps you out. If it does, y'all drop a link, some comments below. I'm really interested to hear back from you guys. I know it may take some time for a few more semesters to roll around, but I'm pretty excited about this, and I hope this helps y'all out. Y'all enjoy.